Today we're going to take a look at problem 16.14. In Professor Fitz's original video, there's a little bit of confusion regarding this even portion. And basically what is said is that with the function we're given, we can't actually get an even function unless we do some shifting, but with the original function that we're given, we're not actually able to analyze it in an even manner. So, I believe that this even portion is a typo, and we're actually supposed to treat it as odd, because if we do treat it as odd, the math and analysis does end up working out. So, for this, we're going to go ahead and analyze it as odd, but the remaining half wave and quarter wave symmetry do hold up. So, first things first, I've got the original graph over here that is given, and then I've just translated that over here so we have a little bit more space to work with, and we can go ahead and start filling in some of these gaps. With the half wave symmetry that we have here, we can go ahead and fill that in. Let's start with the quarter wave. Because then it'll piece together a little bit better. Quarter wave symmetry. Basically, that just means that we can go through and fill in the rest of the portion here. Filling it in like this, right? So we're looking at something a little bit more sinusoidal, something we're a little bit more familiar with. Now, with the half wave symmetry, we basically can do the little flip shift type dealio, where we'll take this portion that is given to us here, we'll move over, and as Fitz does, we kind of get something a little bit like this, and then we just flip that across the x, or in this case, t-axis. So, doing my best to kind of get some of these points here. I guess we can do this one first, and then we get a little sort of triangle going here, and we'll get a little something like this, a little something like this. You know, we're engineers, not artists, but there we go. So now we're definitely seeing something a bit more sinusoidal, and this reveals even more that we're dealing with an odd function, because if we go through and kind of piece together what's going on here to this other side so that we can get this interval from minus t over 4, we've got the 3t over 4 kind of done here, plus a little bit extra. But if we go through and we continue on this pattern to the minus t over 4, we get a little something. Okay, we get a little something like this. There we go. And now we're kind of seeing how that even estimation is not really working out, unless we were to do what Fitz does in the video that he posted and kind of shift our axis, make this 0. However, I'm going to work it in the odd way, because even if we do it this way, we still get some of the in the later portions, that odd property does eliminate some of the AKs, BKs, stuff like that, AVs that we would have to evaluate. But with knowing these properties, we can kind of eliminate some of those, make our lives a bit easier. So, for part A, I guess we're going to draw a little part A here. For part 1, we have sketched out our function. So, throw a box around that. Very nice. Now, to move on to part B, we're going to need to get kind of some function description. We could go ahead and, using the properties that we kind of just talked about, we're assuming odd instead of even, and that changes analysis a little bit, but it does give us some of the same cancellations. With that, we know that our a sub v is going to be 0, and we also know that our a sub k's are going to be 0 for all k's. Even k's, odd k's, doesn't matter, it's going to be 0. So, we'll go ahead and box that up, we're good to go. Then, we also know that this function, as given in the problem statement, we have quarter wave symmetry. No, we have half wave symmetry, and because of that, I'll just throw a little half wave there. Because of that, we know the b sub k's are going to be 0, not for all, but for the even k's. That right there, knowing that the a sub k's are 0 for all k's, that would be one set of integrals and another set of integrals that we have to do for the even and odds. Done for, we don't have to do that. And now that we know that b sub k is 0 for the even k's, that's one set of integrals right there that we don't have to evaluate. So this means we just need to focus on the b sub k's for the odd values of k, which dramatically makes our lives easier. But to go ahead, and I guess we can throw the b sub k formula for the odd b sub k's. We can throw that down real quick just to see what we're going to need. This is normally, it's the 2 over t, but since we're dealing with the multiple things here, it would be multiplied by 2, so we get up to 8. We're going to be looking from 0 to t over 4, and that's just for our original thing that we're given here, and we're going to be basing it off that. The rest of it's kind of just based off the properties that we already established. So we have our function times sine of k omega naught t. And then, of course, what we're actually integrating for. And then just so that we know, this is going to be for our odd k's, k odd. Now, to actually be able to do this, we need to kind of get more of an idea of what our functions are. So we'll come back here, and we're going to go back to like our, more basic algebra skills. We're going to be trying to find a slope here, and the area that we're going to find the slope for is actually this blue portion. This blue, no. We're finding the slope for this portion here, and then we're going to find the slope for this portion here. But first, we're just going to focus on this. So, we're going to use our, y2 minus y1 over x2 minus x1, but for t and for our function. So on top, we're going to get 15. And then at the bottom here, we've just got 0, so that makes life pretty nice. And then we're going to do it for our t's. We have our t over 8. And then again, we're just 0. So that one's pretty nice. If we do that, we'll do our 8 times 15, and I believe that gives us 120 over t. Pretty nice. And then we can say our function of t will equal 120 over big T from 0 to t over 8. Because, right, we're just getting this, we're describing this from here to here. Boom, bam. We've got that. Make sure we remember that. Now, we're going to do this one right here. And this is just going to be pretty much the same thing, but a little bit more analysis because we're not right there at the origin. We've got 20, and then we're going down here to this 15. And then we're going from t over 4 this time down t over 4. We're going down to t over 8. And if we evaluate that, I believe we get 40 over big T. And that will be, this is where we have to do a little bit more. So, we're going to bring back the one thing that we learned from high school algebra, and that would be y equals mx plus b. So our y, we'll consider as 15. We have our m, our slope that we just found, at what x? We're going to be doing at the t over 8, and then plus b. B is what we're actually trying to find here. This is not related to b sub k. This is just y equals mx plus b. If we go through here and we solve for b, I believe we get 10. Very nice. And now we can throw this, y equals mx plus b. Our function of t is going to be 10, which is our b. Just going to throw that in there. And we've got this portion here. And I did forget one thing. Back up here, we have a function of t, but no t here. That just goes there. Forgot to put that earlier, but we'll do the same thing here. 40 over t times t, big T times little t. And then we'll have the range from t over 8 to t over 4. Very nice. Now we could just work with this, but I'm going to do one little step that I like. I just like to throw this together in a piecewise so we can get a good idea that this is describing one thing with two different functions. So again, we've got our 120 over t times little t from 0 to t over 8, just our first portion here. And then here, we'll have our second portion, 10 plus 40 over big T times little t from t over 8 to t over 4. Very nice. So now we have described what is going on there, so we can actually do some of our Fourier type analysis on it. Alrighty. Now, here we're doing 0 to t over 4, but as we just kind of found, we have two functions. So we would need to do one kind of set of integral from 0 to t over 8, and then another set from t over 8 to t over 4 so that we can get that full 0 to t over 4. Let's set that up. We've got our 8 over t sitting out front here. Throw some big brackets because all this stuff is going to be going on. Our first function again from 0 to t over 8. Get that there. Very nice. We'll throw that 120t in there. 120 big T over big T times little t. Alright, and then part of our formula here, throw that sine of k omega naught t. Very nice. And then dt. Awesome, we've got our first integration limits there for that first part of the function. Now we're just going to handle the second function. We'll be going from t over 8 all the way up to t over 4, because again, that's kind of not there. But this is what we have for this given part of the function. Right. We'll throw in that 10 plus 40 over big T times little t. And again, times the sine k omega naught t. Boom, boom. Very nice. And again, all we're doing here is we're doing for the bk, the odd bk. So like our 1s, our 3s, or 5s, continuing on. Now, we have all taken a lot of calculus, but this is circuits. So, we are going to get some help with these integrations because, as we can see here, we have got this one term of t, this other term. That would be quite the integration by parts mess, especially for two of them. So get your favorite tool, Wolfram Alpha, sort of AI help, whichever works for you. But what I end up getting, what we should end up getting, a little something like this. Big T over 4. And then plus sine what's this? That is not a t, that is a pi. Over 2. Very nice. And again, we'll just throw this in here for k odd. That's what we like to see. And again, kind of going with the piecewise sort of deal we did earlier, just so that we can keep this clear and not, get mixed up. The even parts are going to be 0. The odd parts are going to be this that we just found. See if we can do this easy. Go ahead and take that, do a little copy, throw that in there. We'll have this for odd k, and simply 0 for k even. Awesome. And that, yes, that should give us our answer to be Fourier coefficients. Because again, with these properties that we found up here, odd, half wave, stuff like that, that can simplify what we would have to find by a lot. And with the remaining b sub k odd that we have to find, we have found it there. So there we go. Moving on to part C. Now we've kind of done the hard part. Now we've just got some calculator work and some making sense of what's going on here. Again, our even harmonics are going to be gone because it's just 0 for even case. So we'll write that down. Even harmonics say vanish. So we will only have to evaluate for 1, 3, 5. That kind of keeps going on, and as that keeps going on, it will get more accurate to what we have here, and we'll see an example of that in just a second. For k equals 1, basically what we're going to be doing is finding the b sub k values for that specific k, and that is quite literally just taking this 1, plugging it in to these k's here. Just a bit of calculator work. First, I get 19.569. Pretty nice. Now, we're not going to do k equals 2 because we're doing odds. So, we'll go k equals 3. Therefore, our b sub 3 is going to be, just plugging in 3 to these k's, what I get is 0.33731. Very nice. Lastly, we could keep going, but we're not computers, so we're just going to get a good idea of what's going on here. Our b sub 5, plug in those 5s, and what I get, negative 0.1314. 1343. My apologies. There we go. Okay. With these are our Fourier coefficients, and with that, because we're looking at odds here, so our Fourier kind of function is going to be built up of sines, omega naught t. If we were looking at evens, we would be using cosines, but we're doing odds, so it will be built up of sines. And basically these coefficients, we're just going to throw them out front. Sine omega naught t. We've got our first one. Let's go. Throw that. And rinse and repeat, really. I don't like that 0. And for our last one here. Awesome. Very nice. And that should be part C, right? Also, we could have kept going, but the problem just says to do the first 3, so that's a good reason not to do more than that. But there we go. Got that. Oh, thank you so much. Awesome. Okay. Now, for our last part, we're running out of space here. we don't honestly need much more space. But we'll move over here. Part D or part 4, whichever you want to think of it as. Now, use the first 3 terms to estimate our function at t over 4. Okay. Now, basically, we're going to be treating t as t over 4. And omega naught, we know what omega naught is. If we try to, relate it with frequency and period, we would end up getting that omega naught is 2 pi over t. And then we're wanting to evaluate at omega naught t, which is t over 4. So we can just say 2 pi over big T times t over 4. Get them out of there. That's going to reduce to over 2. So we'll get pi over 2. Now, with this, we're basically just going to evaluate everything we have here, but of sines of pi over 2. Small mistake here. Since we have our k's, this is going to be k1. We would need to throw a k in here so that we can account for that k, and a k in here so that we can account for that. But we know what those are going to be. K here is just going to be 1, so we don't really show it. K here will be 3, and K here will be 5. So it would be 1 omega naught T, 3 omega naught T, 5 omega naught T. Apologies for that. But if we go through and say evaluate sine of pi over 2, what's that going to be? That should just be 1. If my pre-calculus is still fresh, that should just be 1. 19.569 times 1. We're just going to get, we'll throw what we're trying to find here. 19.569. Awesome. Because that is just times 1. Now, we're going to go through and do the same thing, but for this sine, now it would be sine of 3 pi over 2. And as our sinusoid does, we're going down below, so we'll get -1. Now, we'll take this 0.3731 multiplied by -1. We're now subtracting. Interesting. Now, we'll do the same thing for the 5. And that should be positive because, sinusoid, we're going up, down, up, down. So, boom, boom, boom. I'm just going to do a double check real quick. Throw that in the calculator, and yes, we get 1. So, -0.1343 times 1, -0.1343. Very nice. And this is approximate. We are trying to evaluate a real function with some analysis techniques without going to infinite levels of precision. So this is an approximation. And when I throw all of this together, I get 19.062. Awesome. Now, I do, the solutions are great, but they do sometimes contain some errors. I do believe that the solution manual gives 19.81 for what is supposed to be here. And I guess we can throw that over there because that's where it's supposed to be. However, if we do take this stuff here, and instead of getting -1 for this value here, say we accidentally did pi over 2 again, we get 1, and we add, instead of subtracting this value, we do end up getting 19.806, which would round to 19.81. So, the solutions manual, while its value is a little bit higher, I do believe it's just from this false or incorrect evaluation here. So, just something to know. Now, trying to make sense of this, we have our function that we just evaluated at t over 4. We get 19.062. We should be able to go back to our graph that we looked at earlier and just look at it at t over 4. We technically, we wouldn't really have to do this. However, if we wanted to go, given with this information here, if we wanted to go to anything past t over 4, we would kind of have to go through and do this analysis, because we don't, unless we sit there and drew out a whole bunch of things depending on these properties that we were given. We could do this analysis, have a computer do it for us. 19.062 is not quite 20. However, we only did the case for the first 3 odd terms. This keeps going. This keeps going. Say we wanted to evaluate b of 7. B of 7, right? And I do believe I went through and got this earlier. Yes. B of 7 is looking to be 0.3993. We'll go ahead and call it 399.39936, We'll round that 3994. Now, if we were then taking that and we do, those are some great looking 9s. And then we do sine. Now instead of 5, we would have 7 omega naught t. Omega naught t we evaluated to pi over 2. If we go through and do a sine of 7 pi over 2, this come -1. We'll now add to this. We'll show it in a different color. We'll add 0.3994. That brings us back up a little bit. 19.062 plus 0.3994. We're at 19.46 now. This gives us 19.46. With that, we are getting closer to that, 20. We're getting closer to that 20. And again, this can just keep going for multiple iterations. And as we add iterations, we should get a little bit closer to that 20. But this is just to kind of show that if we do not know what the rest of the function is doing, based off those kind of initial sort of conditions and properties that we know, we can work out a way to find other values, even if it's not just t over 4. And that's pretty nice. We'll leave that there. So, this should be the work for 16.14. But I know that Professor Fitz, in his version of the video, instead of, working it as odd, he then shifts it to become even. And I guess we can show a little bit of that. Instead of having our 0 here, we then kind of define a new 0 here. Then this 0 here would be our negative t over 4. Yes. And then this would be a positive, I believe. Positive 2 over 4. Anywho, by doing that, he was able to get pretty close, but there was still a little bit of confusion towards the end. And I believe where that confusion, I'm not going to work through that whole thing. I'm just going to give my 2 cents for what it's worth on what he got. We'll get a new page in here. Got the little snapshot of what Professor Fitz got. Now, where I believe the rest of the fault kind of came from was from this little portion right here. This little portion right here, the evaluation of this other side. Alright, I had to do a little double check just to make sure. Okay, so yes, the problem is originating from what what Professor Fitz ends up getting here. If we go through and use our method for finding the slope to evaluate what that section should be for the even shifted function, we should get our starting point here. We're evaluating this portion right here. We get 0, our y2 minus our y1 of 15, over, not these ones, but these ones, our t over 4 minus t over 8. That should give us we would get the minus 15, and then this would give us t over 8. And if we evaluate that, we would get 120 over t. We have that. Now we need to do what we did before, where we find the b. Our b would be 15, starting there. Our 120, we're trying to find the t over 8 plus b. Those get a cancel. Minus 120, that's going to give us negative 15 plus b. Add that over. Therefore, our b is equal to 30 instead of this 15 here. But pretty much the rest of it is the same. We'd end up getting 30 minus 120 over big T times little t for this portion here. For it'd be t over 8 to t over 4. So, with that correction, I do believe that is all you would need to be able to follow the rest of Professor Fitz's video, and that should get the correct, coefficients that we get here, and then evaluating should give you the same thing. Not fully worked that through, but I believe this is what gave Professor Fitz some of the troubles whenever he was working out the solution. So, while I do not have the same amount of experience that Professor Fitz does, I do have some experience working homework problems and working through solutions. So, I do hope that this video was a little bit helpful in working out this problem, and thank you for watching.